have our first speaker, Ariel Goobar, who's going to tell us about time domain cosmology in the era of large-scale surveys. So, thank you very much.
Thank you very much, Jackson. Thank you for inviting me. It's lovely to be here and talk to you all about the very big excitements of time domain astronomy, how it sort of affects this kind of questions we all in this room are interested in. It's a bit daunting, though. I just look at the Copernicus here watching over me. I never give a talk watched by Copernicus, but it should be okay. Let's see. So what you're watching here is, should you give you a sense of the development? This is the number of optical transients, most of them supernovae, discovered since 2016. So this is the number of supernova that the community is finding for the last few years. And I will try to address how that relates to the kind of tensions and anomalies that we are interested in here. First of all, it comes in two very important topics. One is the Hubble tension, where, of course, type 1a supernovae, one of the many dominating dots in the previous plot, are very much involved. But as you know, what I'll be alluding to, these results are based on much, much older data. Okay? So, of course, everyone in this room knows there's this 5 sigma tension. I will not spend much time discussing it. There's this other thing that came up only, I don't know, a couple of months ago, which is the DESI results came out, of course, mainly based on baryon-acoustic oscillations. Again, I'm sure someone else will be talking about this. But I will touch upon the fact that the significance of the deviations from lambda CDM came when the supernovae were added to the sample to get a CMB. That really gave the 3 sigma effect. And I will begin discussing what kind of things we need to watch out for there. So yeah, so related to that, these two things have in common is that the supernovae which are being used are very, very old samples in most cases, in particular in the low redshift domain. That's what I will be focusing on. The high redshift supernova is one thing, but what about the low redshift supernova? And I will sort of argue for why we need to maybe revise this or just look it over again, make sure that there is not a mistake there, okay? So this is sort of the SHOES results, right? So these are the supernovae which have a Cepheid, which has Cepheid variables in their host. So if you look here, some of the supernovae are from the 1980s. So I just get an idea. How many people in this room were born after the first supernova here? How many people are born after 1981? It's the vast majority. Good, good. So I'm talking to you. So this is another result, which is, of course, I mean, it goes with the territory. I'll be fair here. I mean, these are supernovae. The distance to where we can observe Cepheids, it's only about 20 megaparsecs. So this could not have been done any differently. This supernova happen once a year or so. So there is no, I'm not claiming there is, I'm just saying that it's a fact, right? This thing, however, is more interesting. These are the Pantheon compilation, and this not only includes supernovae at the very local. Here there are supernovae that is very easy to find. Yet the most, the results, the data that people are using to constrain cosmology is based on a compilation of, in this case, 25 different photometric systems, okay? In the low redshift domain, that's actually kind of insane. If any of you guys have ever worked on data, maybe you realize that you do your best, but it's very, very hard to, prove that you got things calibrated at the sub% level when you're combining so many different data sets. So, all right, so let me take you, so where does this have to do? Again, more on cosmologist thing. This is the lambda CDM plot from the DESI 2024 plot. You see that as far as we look at WCDM, when you put it all together, it all looks very much like lambda CDM. There were no surprises there. You probably know this story, right? BAOs are these things. The bananas, oops, it's hard to move. Let's see. The bananas are the supernova results. CMB is this one. And what you see here in the resulting, the concordance model really looks very nice like lambda CDM. And these are the parameters. However, this was the surprise, okay? That when you move over to these, adding one more parameter, and again, I'm assuming most people are familiar with the CPL parameterization, There is they try different supernova compilations to combine with the data, and you can see that there is a shift from lambda CDM, be it 2.5, 3.5, it depends a little bit. So what you can see here, by the way, is that, okay, here's the parameterization, in case you've forgotten about it. And one of the things I will actually, it's maybe hard to see, but the values of omega matter actually are kind of different depending on, there's a bit of a tension between the data sets when you add another parameter, in this case, WA, and you can see that kind of interestingly, the omega matter kind of moves around a little bit, and we'll see how that plays. All right, so this is another way to look at this. This is, again, just putting my supernova-centric hat here. Say, okay, this is the kind of supernova that this is based on. This is the dark energy survey supernovae. And what I'll be focusing on is at the bottom here. As you can see, and I think it's very hard to see, and that sort of illustrates my point here, that the difference between these different cosmologies is really the difference. You can see at high redshift, these things, you cannot. So the green is all right, let's see, which one is it? So the red thing, I guess, is just lambda CDM, flat, and the green thing is this other more funky W0, WF thing. And you can see the difference is really at the low redshift. Very, very small, tiny things, okay? And I was going to give you a little bit of interactive things, just to give you an example, how you can, I'm not claiming this has to be what's going on, but how easily it is to get your cosmology wrong if it happens to be a problem in this. What I'm showing here is a mock of the data we just saw, okay? And I'm mocking it such that it's at lambda CDM. I'm just going to see how this thing moves in parameter space when I start introducing by hand, arbitrarily systematics. I'm not saying that any of these things have to be, but I just want to give a sense of how easily you move around here. So for example, if I have a mismatch between the, sorry, where is this thing? Oh man, here, okay. If I have a mismatch between omega matters between the sample, this thing moves in this direction a lot. I can reset this thing again. If we have a calibration error, it was saying, well, you can see how this thing moves like crazy. I'm talking about, in this case, 4% calibration error, 2%. What do I mean by calibration error? I mean how well you combine the low redshift data sets with the high redshift data sets. So if you're 2% off, you're off, okay? And another one we can try, what happens if I, very trivially, there are two different calibrations for how you correct for Milky Way extinction. These are two things, nobody knows which one's right. I just take another one, and then the thing moves. So I can get these things to match with DESI with very, very trivial systematics, okay? I'm not claiming this is what's happening, but I just want to impress on you how important it is to keep this thing controlled, okay? Super important. It's impossible to use this data set as it is to claim that these things I'm showing you are not happening, okay? All right, so we can move on. So the rest of my talk, I'll be focused, and we can go back to this. If you're your favorite systematic, we can discuss it. But by the way, I should give credit. So this is a tool we put together with, the people listed here, my former postdoc, Suhail Dhawan, myself, and Brody Popovich, just to give an idea, and we're writing a paper about how these things can move. But essentially, the tool is there, so if you guys want to, we can check this further. All right, so what to do about this? And as I said, there is something we can do about it because we are in the era of large surveys. We don't have to rely on this old data, 25 different field systems. It's pointless. Why do that when we have new data sets? And this is what I'm going to focus the rest of the talk about. And this is a picture I was thinking. So this picture I downloaded from the Transit Name Server on a couple of weeks ago. It would have been fun to show you how it compares to today, but it doesn't matter. Things happen all the time here. So the survey I'm working on, and it's actually, well, if you go back here, the survey that actually contributes the most to this data is the Swiggy Transit facility, which has been running since 2018. Some of you may have been there. It's at the site, which is in Palomar. We have a survey telescope over here. Oh, it's hard to point. It's here. And then things are classified over here and here. So it's all, at least there are two, it's very robotic. So there are very few humans involved. And we are finding supernovae all the time, and this is the happy people pointing at their favorite, most recent supernova. I'm just come from a meeting in Stockholm where we got together. But why are we finding so many supernovae? What's happened is that the camera, there is, as always, when there are new breakthroughs, it has to do with technology. The technology breakthrough here is the camera size. So what you see in the middle is the size of the camera we're using at the 1.2 meter telescope in Palomar. It's a 47 square degree camera, and for just getting a sense of scale, I'm putting our nearest neighbor, Andromeda galaxy, and you see Andromeda fits into just one of the, essentially one of the small sections of our camera. And it's the biggest one. You cannot find a bigger camera than that. So we are in the process of releasing the first set of data. So this project has been running for nearly 7 years, but we are releasing, finishing the analysis on the first 2.5 year data. And again, to give you a sense of scale, the data set I was showing you before, where I was showing that it's kind of iffy whether you trust or not these low redshift data points. In that plot, there were 192 supernovae, and out of the 1829, the rest was high redshift, okay? So the survey I'm talking about only adds low redshift, okay? So the yellow is to be comparable with yellow. So our so-called data release 2, which is, again, I remind you, 2.5 years out of 7, it's already more than an order of magnitude, more data than it was combined from these gazillions of systems for many, many years. And there, for those of you who've been paying attention to the archive lately, there are a lot of papers coming out about presenting elements of this data set. All right, so why do I put a lot of faith in this data? Well, the data quality is very, very good. It's one instrument, we get every supernova the same thing. And we have a range of quality, but just to give you an idea, so this is what we call sort of worst quality, this is our average quality, and some of the supernovae are just insanely well sampled. I mean, this is so well sampled that it's sort of a waste, it's kind of a waste, but some of them just happen to be in the region where we're hammering the sky all the time. But the data is pretty amazing, and we have 3 filters. And again, to impress on you how good this data is, this is all the data just stacked together. And this supernova just sort of sit dead on, the template. So they are very, very, very good data. And every supernova has a spectrum or multiple spectra. So we know these are type 1a supernova. There is no ambiguity there. And this is the Hubble diagram before we standardized. As many of you probably remember, we sort of maybe some of us say that type 1a supernova are standard candles. Of course, in reality, they're not perfect standard candles. We need to calibrate for color and light shape. So before you do any corrections, this is what a Hubble diagram looks like. You have some redder, fainter supernovae. So going up here is faint. This is the redshift. Going up here is faint. C is the color. It could be a mixture of extinction or intrinsic properties. But what you can see here already that at some point we start to be, the selections kicking here, right? So we have very good understanding of selections. We know that up to about redshift 0.06, we have every supernova there is. We don't, essentially, we don't lose anyone. So when we talk about volume limited, we really even ignore all this data set here. We said, let's stick to the redshift 0.06 and lower, where we essentially, our systematics in terms of selection effects are minimal. And this is what left. Once you apply these corrections for light of shape and color, we're getting this very, very nice Hubble diagram, which I think will be used in the future by many of you, I hope. All right, so I'm not quite ready. We're not quite ready to do cosmology with it, and I think that should also be impressed on you that we've been working with this system for 7 years. Okay, this system alone. And we are not yet there to deliver sub-percent precision. We know we don't have that, okay? But we know how to get there. But I want to impress on you how difficult it is when you want to do precision cosmology. It's very hard to just grab systems from disks and think you can do it. We know we cannot. And we're working very, very hard on achieving better than 1% accuracy. And part of the story is to how to calibrate these things. There's something called scene modeling, which involves really using all the data and not just doing subtraction, but I don't know how many people you work on this. There are two ways to do this business. One is that you subtract the galaxy from the supernova and you measure the flux of the supernova. But then, of course, you're stuck with the problem that for calibrating, once you subtract the images, you lost all your stars because those do not change. And then you lost all your precision. You lose your absolute knowledge of your accuracy of your photometric calibration. So we're working very hard on doing this the right way. Then we are working hard on combining, as we're saying, the crux of the problem here is to combine the low redshift with the high redshift. So there are two separate efforts going on. One is to take our data and combine it with the dark energy survey high redshift data, which I was showing before. And again, the emphasis is here in making sure that when we combine them, we don't have 1% off in relative calibration, then we are in big trouble. Okay, so we want to avoid that. The other effort is actually quite interesting. There is a completely pristine data set which has been obtained at high redshift, with a supernova telescope. That is actually an amazing data set going all the way beyond redshift 1, and there are 600 supernovae that has never been used. So one of the efforts will be using an entire pristine set of supernovae, which none of the supernovae has ever been in the Hubble diagram before. So when that result is presented, it's completely independent of all the other ones. Because otherwise, there's this worry about, okay, you're presenting a data set, but you have an overlap with the old one. How correlated is this? But the second data effort is completely unrelated. And of course, ultimately, we think the ZTF data should be a perfect match when combined with LSST and Roman. So, at one point, we will have an absolutely spectacular low plus high redshift data set. So this is a little bit of what I was alluding to. This is work in progress. This is our data set from DR2, as we call it, and this is a sort of a simulation of the Subaru data. And I should say it's Subaru data plus 1 year of supernova legacy survey that was never included in previous results. So this is something to look forward to. And then let me connect it with some of this, connect it a little bit with the, how does it fit in with so that's what I've been talking so far is how we plan to revisit the DESI results, the potential, hopefully confirm that these claims or this potential discovery that the equation of state of dark energy is dynamic, we hope to see that. But then let me remind you that we have this other tension, which is, of course, the one with many people in this audience have been working on, which is the business of how to compare the distance ladder with the generally speaking, early universe results. And there, of course, the problem is more complicated because it's not only, of course, the supernovae are just one part of it. It's this part, right? But before getting there are you have geometric anchors and you have Cepheid distances. All of those things are needed to calibrate the brightness of type 1a supernovae because we know type 1a supernovae are wonderful distance estimators, but we don't have a priori knowledge of how bright they are. In order to get the Hubble constant, we need an absolute distance. Hence, we need an absolute knowledge of how bright these things are, which, unlike the case I was showing before, the case for dark energy does not require having knowing. We just need this is a relative measurement. This is an absolute measurement. So, so where are we with this one? Of course, well, both Wendy Friedman and Adam Rees will be talking about this. I will be very, very brief here. But the point is that that some people have expressed concerns about, for example, using Cepheids to do this calibration. There are sort of two main reasons to worry about it. One of them is that the Cepheids are found in only some of the galaxy populations where we find type 1a supernova. And we know these populations have differences. So again, as I was alluding to before, these things are not perfect standard candles, and there are some dependencies on the brightness. And it doesn't take much to go wrong here. So there are some worries about using Cepheids as the way to calibrate type 1a supernovae. Some of us have also another worry that the Cepheids are found in very crowded, dusty regions, and it's notoriously hard to correct for extinction by dust because not every galaxy is the same when it comes to dust. You know, just like everything, galaxies have evolution, and dust grains evolve just like galaxies do. And again, this is sort of some debate in literature. I happen to be concerned about how this is corrected for. So what we are trying to do with ZTF data, just bring it back to the story, is that we want to try to, again, minimize the number of instruments used here. So, okay, so as I was explaining to you, we have a Hubble diagram, then we have completely different supernovae that are used to calibrate. The ones I was showing you, most of you were not born when the first supernovae were found, right? Those two things have to be connected. With ZTF, we hope to avoid that thing. We want to have the ones which we use for calibrations and the ones in the Hubble diagram, they should all come from our sample. But then we need to use a different way to calibrate these things because, as you know, the shoes has demonstrated, Cepheids, you cannot find, the volume is too small. But there's another way to calibrate these things, and Wendy Friedman this afternoon, I think we'll be talking a lot about it, so I'll be, again, just brief about it. It's called the typical red giant branch. And we already are making some first measurements where we combine the type 1a supernova from ZTF and, you know, beautiful data set over here, and then we use space measurements where the sort of the distance, of, you know, so the absolute brightness of some supernova here, the supernova here is calibrated with these TRGBs, and we're starting to get our first results on the Hubble constant based on one data set plus space. You know, eventually, of course, we want to do better than that, and we are hoping to use something like 40 supernovae with TRGB distances, which we can do, not with HST, but with the newer telescope, James Webb. And so in principle, it is a matter of combining our data set we have today, getting enough time with Webb to do this absolute distances, and then we should be able to compare our results with shoes in a completely independently. Well, with shoes and with the Carnegie Chicago Hubble Key Project. So a little bit of where we are and where we're heading. So I just mentioned to you that this summer we are releasing something we call DR2, data release 2. There was a DR release 1, which released, led by my postdocs who held the one at that point, but this is like many times larger. And as you can see, there are more supernovae in that data release alone that everything has been published in 20 years of data set in type 1a. So this is here, this blue thing. But as I was alluding to, this is just the data we are now ready sort of analyzing, but there is a lot more on disk, okay? So we know that we have 6,000 supernovae already in the can. We keep running, we're finding things all the time. So should be, probably we'll be hitting something like 10,000 supernovae before before LSST kicks in, I should say. And that's only a subset of the data, because that data set only includes the ones where we got a spectrum. So we found a transient, we move to the next telescope, we take a spectrum of it, we know it's type 1a supernova, thumbs up, it goes to the database. But there are many, 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 many more supernovae, fainter, for which we just don't have enough time to get spectroscopy. But we know that the vast majority of them are type 1a supernovae. So we know that there are, if we do a photometric typing, which is, by the way, something that was used by the Dark Energy Survey for the redshift. So identifying the supernovae, not exclusively by the spectra, not by the spectra, but using only the light curves, because it turns out that supernovae of different kinds look different in principle without biasing yourself in terms of, you're not using the brightness of the supernovas, you're not biasing yourself in that way. Just looking at the shape of the light curves and in different colors, you can actually identify them photometrically, and we already have, we think, about 50,000 of them, and we, by the end of the, within, as you see here, by the end of next year, we think we'll be hitting something like 30,000, 40,000 supernovae. At that point, you can ask yourself, okay, why bother? If you have so many supernovae, at some point it's relevant, but it's not, because I go back to where I started my talk, systematics. One of the things you can do when you have so many supernovae, you can divide them in subpopulations, like the ones on elliptical galaxies, the ones on spiral galaxies, the ones the northern hemisphere, the ones, you can start dividing them in subsets. And of course, if everything checks, the answer should not depend on any of those subdivisions. So I think this added data set, although it might seem like an unnecessary luxury, is actually pretty important to get confidence in if there is indeed, if we really have to abandon lambda CDM, I would do it much rather after we checked all these things. The last thing I want to touch upon before I close, and I think I'm doing okay with time? Good. So one of the things that's very, very dear to my heart is, and it's also very much related to the fact when you're looking at these very large cameras, is that once you have such large surveys of the sky, not only do you find a lot of the things, common things, but you start to find a few of the very rare things. And in this case, this is strongly lensed supernovae. So I'm actually showing you both the things we've found from Palomar, these two supernovae, and also just for comparison, I'm also showing something which was found from space with the Webb telescope and again, all beautiful things. What you see in all these cases is that one supernova produces multiple images. In this case, 3 images. In the case of my two favorites, Zwicky and 16GU, each one of them produce 4 images, okay? And what you should notice here is the different scales. So whereas clusters, are big things, bend light by a big angle, galaxies in general bend light, the direct trajectories of light by smaller angles. And in this case, it's actually pretty neat, okay? I show this just to impress on you that 1 pixel in ZTF is 1 arc second, okay? So these things, they all fit in with 1 pixel. So how could we find these things? We certainly didn't. This is a space image after we said, all right, I know where it is, point HST in this direction. We find these things just because these things are standard candles, meaning we know how bright they are, and once we have a redshift of this thing, in this case, let's say 0.49 and 0.351, well, we know that we don't find these things with ZTF that far. The telescope is only 1.2 meters large, and the pixels are the site is, just 2 hours drive from San Diego and Los Angeles. This is not, you don't find redshift 0.4 supernova there unless you're lensed. So once we find these things, we go for them with a high spatial resolution. And just again, this is a pretty plot by Nick Aronson, a postdoc working with me. And you can see the different scales and the redshift. So these are the supernova lens supernova we've been finding from the ground. And these are the ones you might have heard about, supernova Refstal and supernova Hope. And of course, the exciting thing about the ones on the top is that values for the Hubble constant have been extracted. And for those of you who may or have forgotten how that works, the story is the following, that again, the images are split just because there is an intervening deflecting object, either a galaxy or a cluster of galaxies. The light follows different paths, and that means that there are 2 things that are going in there, the path lengths, but also the gravitational potential affecting the time, the clocks, or affecting the time of where the light goes through, and hence you get different times between the images, and these times are scaled with the absolute scale of the universe. So you can actually, or sort of the inverse of the Hubble constant, I should say. So hence you can measure these time delays. You can measure Hubble constant in a completely independent way compared to what you do with both the CMB or the early universe with lambda CDM or the distance lambda. So this is very neat because it gives you a completely different look at it. And I guess what I will, and maybe of you know this has been done quite a bit with quasars, but although there are only 7 quasars so far, or 8 perhaps now. But why are supernovae cool for this? There are a couple of reasons. One is, as you can see here, is that unlike quasars, supernovae fade. And one of the problems we have, so the big problem here is to model the length, okay? Measuring the time delays is what it is. You have to do your best and try to measure, but modeling the lens, that's much more of a model. I mean, there is a model there, right? So it's sort of challenging. And supernovae have one advantage compared to quasars, which is that the supernovae go away, the lens and the host galaxy around it, the host galaxy of the supernova are exposed to you, so you can do your modeling both with and without the point sources. So it really gives you a very nice, clean shot, and it's actually a lot easier to model the lens. I should also add that in the previous cases, where I will be coming back to that, where we have measurements of the Hubble constant, they've all been with cluster lenses, and that is notably difficult in the sense that clusters are complicated objects, could be a lot of substructures, so it's not all that easy to be sure, again, that you model your lens perfectly. Galaxies are simpler. In that sense, there is one added benefit of having using galaxy lens supernovae. The other thing, of course, is that finding these things, the monitoring is very short. Supernovae only live for a few weeks. So, you don't have to monitor, quasars you have to monitor, since they're just random walk, right? These light curves. You have to monitor for years and years, 10 years, in order to get time delays. With supernovae, once you located one, you know that you're on it for 3 or 4 weeks, maybe a couple of months, and you're done. And the light curves are very smooth. So there again, I was showing you before, this type 1 is supernova, we know the light curves perfectly, so we can fit them, and that's a pretty good thing. Supernovae have another benefit compared to quasars, which is, again, going back to the business of the R standard candles. So we can also use the magnification to model lens, not only the positions, as you can only do with quasars. So that adds something. So this is how we measure the time delays. These are a couple of examples from supernova Hope on the left, and this is one of our ones in the we found from Palomar. So you can measure, you can see here the different bumps from different images. You can see how you can extract the time difference between images. This is the same supernova, right? And it just going, you see it going off at different times because of what I told you, the path lengths and the Shapiro effect. And then you can extract the time delay between the bumps if you want. There's another way, again, which is unique for supernovae, which is if you take a spectrum of a supernova, you can date that spectrum. It's an expanding photosphere thing, and as the photosphere is expanding, you are peaking further and further and further in at the explosion site. And it's a homologous expansion system. So the closer you look in, the lower the velocity is. So by measuring the velocities of these features here, you can actually extract the phase of the supernova. And again, you have a completely independent way to get at the time delays. So again, it offers a two-way path for getting the time delays. And as I was alluding to, you can, there is a relation between time delays and the Hubble constant. Again, of course, there is a modeling here. You need to infer the properties of the lens. So this is where things are, pretty exciting. Everyone knows about the Planck versus shoes. It's here. Today we'll also hear from Wendy Freeman, which is kind of in the middle. And again, so the two cluster lens supernova, they also put themselves on either side. So far, we don't know. I mean, the error bars are large, that everything is fine. But we just started this business. This is about to explode. So I'm showing you this not because I think you should be particularly impressed by these two numbers, but just to show that the method kind of works, and it is about to explode. One of the reasons it is about to explode is because LSST not only will be a wonderful survey for every, possibly for every science that most people here care about, but it is really a discovery machine for lens supernova. We will be finding, easily, lens supernova week. Well, let's see. There will be lens supernova week. It's up to us to find them. There's a big difference. In fact, there will be lens core collapse supernova, the ones which are tougher to find because those are not. Well, those are easy to find, of course, if the images are split. But if they're all sitting in the same pixel, that's much harder to identify. But there will be one such thing every day. So it will depend on our ability. And here there are, of course, wonderful synergies between LSST and the space missions going on, right? Because even if you don't see multiple images in LSST, for example, there's a fair chance that Euclid already looked at that patch. And even if they haven't seen the two images of the supernova, you can see an arc, right? You can see that there are the galaxies where the galaxy where the supernova is sitting is strongly lensed. And hence, when you get a supernova there, you need to watch out. That could be exactly what we're after. So maybe I was speaking a bit fast. I'm actually getting to the end here without, anyone having to ask me to shut up. So I want to say that, so we are facing important challenges to London CDM. And so the word of caution from my side here is that, look, we need, whenever the tensions depend on supernovae, it is better, in my mind, to confirm that with newer data sets where enormous attention to details is being paid. We are paying enormous attention to details, to the selection effects, single instrument. The calibration is just, we have an army of people working on the calibration. It's a very different game than just taking a data set from someone's disks and inferring precision cosmology. So I do think that we should expect in the near future a very big impact in precision cosmology. I also, sort of, again, the other part of the story is that because we're doing these large surveys, strong lensing is about to experience a new, I think, an explosion, really. And I think again, in particular, the combination of LSST plus space missions will probably give us a very, very exciting measurement of Hubble constant in the near future. And again, I hope you all agree with me that the golden era of time domain surveys is here, and it should be important for cosmology. Thank you.
Thank you so much. Any questions, comments? Thank you so much. Any questions, comments? Yep.
Very nice talk. You had a very nice tour at the beginning that
Yes.
you changed some parameters and now see the contour move down. That was fantastic demonstration. So I want to ask, so at the beginning you also mentioned that at low T supernova data might be old data. So which parameter, if you tweak around, that's going to solve Hubble tension or temper or
right? So I was focusing on the latter, on the evolution of W, and there I think I hinted at it, but I was subtle about it. So two things: if you accept that there could be a miscalibration between the low Z and the high Z by 2%, and if you just opt for another parameterization on the Milky Way extinction, which is it's 50-50, you can go for every one, then you get dead on what the DESI thing. When you started, mocking lambda CDM data set, and then just wrongly assigning these two things. So it takes, my point is, and could be that, could be something else, or could be, my point is, it's so hard to rule out. That's my point. For the Hubble tension, I think is different. As you said, this was W, not WA. So it was not addressing that point. For the Hubble tension, I'm worrying about the things I mentioned, that the Cepheids and the fact that, so it's a calibration. Again, it's a different story, the absolute calibration. So that was not addressed by the little tool I showed before. But we can talk about it. Yeah.
Thank you for the nice talk. You said that there is a very efficient way to identify systematics by grouping supernova into groups and finding if you get the same calibration parameters. Now, there are two questions I have on that. First of all, have you implemented this in some groups already? And second, there has been some studies by, for example, Radek Votak a few years ago, where he pointed out that, in fact, if you do that, you find a significant mismatch in the color parameters of supernova, which could be, of course, interpreted as a systematic, but one could also think otherwise. One could see it as a useful signal of perhaps having.
No, I don't disagree with anything you said. My point is that we already have 10 times more data than anyone. And for one instrument, my point is that when you compare data sets from two different instruments and you find differences, I personally do not know what to make of it, because, you know, having worked with data for nearly 30 years, type 1 instrument, I know how hard it is to calibrate these things. I don't, you know, you show me a 3% effect, I tell you, I know, I can show you how you get to that. So my point is, everything you said, I agree with it. With the ZTF, we haven't looked at those things yet. We don't want to bias ourselves. We want to really put everything out there. And again, we haven't unblinded anything. You know, we really don't want to do anything until we are dead sure about, we trust the data before we get carried away doing cosmology. So, but we will do that. Rest assured, yeah.
Thank you for the very nice presentation. This question is kind of related to the past too. And so in the beginning of your presentation, you argue that it's very difficult, or there's a lot of things that can go wrong with the supernova analysis. For instance, the observations can be bold. It's difficult to cross-calibrate the metric systems. Can you clarify which particular evidence really points to one of those issues being potentially being an actual issue?
So can I point to what's the name again?
The evidence that
well,
points to one
evidence is, as I said, you know, I based on experience that I think it's very, very, very hard to get 25 filter systems to be matched without, you don't have any, the evidence is on the other side, right? The question is, how will you convince people that lambda CDM is wrong if you cannot demonstrate that the calibration is correct? And I would argue that I don't think that anyone combining 25 systems, which were taken by different observers, some of them, you know, left the field a long time ago, I think that the burden of proving that all of that is right is just impossible. That's my point. So again, there are many, many ways to get calibration wrong. We know, for example, as I said, with ZTF, this is a system we know and love. We've been working for 7 years. I can make a long list of things that could go wrong, but I'm not going to say anything bad about the other people. It's not that I want to say that the data is problem. I just don't know. I don't know how you can convince yourself that there are not problems at the 2% level. That's what we're talking about here. Yeah.
Just really quick. So, what would help convince yourself that some of the analysis is correct? For instance, what would it take to convince?
I think I went through that. I think the data set we have has all the potentials for us to demonstrate to the community that we understand our data set. And as I was saying, we will divide it in multiple line of sights, etc. We will try to understand how different things are. And as we just heard, whether we find differences or not, we'll see what we do with them. But right now we're assuming, there's an obvious thing, right? For example, just to give you an example. If you take the Hubble tension, right? Things are assumed like the extinction laws in Cepheids are all like the Milky Way, right? For the supernova in the same data set, we assume a completely different extinction law, completely different. So for the same galaxy, you're assuming the dust to different things, to the Cepheids and to the supernovae. I mean, there are things like that. We can go make a long list. So I'm saying there are so many assumptions which are, might be okay, but I don't see why I should try. I should be convinced. Yeah. So many things like that. So I'm a skeptic personally. I came out of here, so I'm less convinced about the Hubble tension than Adam will be arguing, and he knows about it. He will be arguing tomorrow, yeah.
Hi, thank you for the talk. So looking at the future and the impressive number of supernovae that we expect from LSST in particular, what kind of results do you expect? And if I'm going to put it down around it, do you think that the systematics are going to kind of dominate the error bar very quickly and we won't get very tight constraints in particular? Like, I'm worried about the modeling based on what we're showing before.
So there are a couple of things which I'm particularly excited about in LSST when it comes to, let's say, type 1a supernovae. One is that going back to the thing, what happens when you find many, many, many objects? One of the things we start finding is that you have the same galaxy is hosting 2 or more supernovae. 2 or more type 1a supernovae. So these things I was just discussing about like, oh, how well to be correct for things like the color excess, extinction. Once you start having multiple supernovae at redshift bin after redshift bin, you can fold that completely out of the question. You can extract those correction factors, cosmology in a completely distance independent way. And there are tricks like that you can do. So I'm kind of confident that once you have these huge data sets, going back to the answer here, you can start subdividing the data in many, many subsets, which allow you to check for systematics and control them in a completely different way. So I'm actually pretty excited. I don't think that we need to be stuck in a situation where I'd be skeptic. I think I think the future looks pretty bright. I think we have data sets to control, to measure and eliminate systematics.
Has there been any forecasts?
Many forecasts. I'm not that I am involved in any of those forecasts at the moment, but so I don't know. I would have to. I don't know actually. The specific papers to point you to, I don't know. Again, if you care about some of the systematics and worry about, you can watch. We have this. We call them siblings. These multiple supernovae on the same galaxy, and one of the Astro PH papers I showed you was that. And I think that shows you very, very nicely how we can check this standardization of supernovae in a completely independent way, and we're actually very nicely finding the same results in both ways. So that's good. So I don't know. No, so I don't have any specific percentage to quote here. I don't.
For very small redshifts, do you also have to worry about the proper motion?
That's good. Good question. Yeah, at the very, very lowest redshift, we do, right? So yeah, so I was telling you that we have volume complete up to redshift 0.06. At 0.06, proper motion is negligible. But yeah, I mean, once you start hitting, say, 0.01, etc., then proper motion is of course something. But we tend to think about it differently. We think that this peculiar velocities is also an interesting cosmology tool. This F sigma 8, etc., and how these things move around, what you can extract from that. It's a problem, as you say, for the Hubble diagram, but it's an independent tool if you want to probe the growth of structure. So there are ways to use it to your advantage as well. And if you worry much about it, you just move your lower redshift bin a little bit higher up.
Okay, so maybe
Thanks. Just a quick comment. Supernova is obviously important, but when combining Planck CMB observations with the DESI recent data, we can still obtain 2 sigma evidence of a quintessence-like signal. That's just my comment. What do you think?
No, I think it's great. I'm saying that. No, and I think I said in the beginning that there was a signature, and as I said, I assuming someone was going to talk about it. I'm just saying the thing moved to 3 or 3.9 sigma once you put the supernovae. Nobody will be more thrilled than me if it happens to be true. I think one has to be careful. So yeah, hopefully that survives. Yeah.
Okay, thank you.
Okay, great. So let's thank Ariel again.